Florey didn't even consider solvents. And he got actually Nobel Prize for this theory. And for non-polymer systems, the view was and is that the only role of solvent is to dilute these repulsive contacts between different polymers. Of course, afterward, people tried to use this model to describe aqueous polymer systems, and it usually failed. And the reason was the theory was not developed for polar systems, so forget about water. But I'll give you one example that I think tells you all. Here is the example of polyvinyl alcohol with dextran, and in dry state, X-ray diffraction shows that polymer are completely miscible. There is no repulsion whatsoever. Nevertheless, when you add water, they phase separate. On the right, at the bottom, the figure shows phase diagram. I'll show it. The typical phase diagram in water for two polymers is here. It's for dextran and phycol. Basically, every point below this curve, which is called binodal, there is no phase separation. It's a single mixture. When you get above binodal, say point D, it will separate into two phases, the composition of which you can get from this phase diagram. The interesting point is that, like at point A, for example, you can move along the it's called tie line, the direct line that binds composition of two phases and composition of initial mixture. You'll get always the same composition in the phases, only the ratio of value will change. And in the end, as you can see, there is a vast variety of two-phase systems you can form in the same type of mixture of two polymers. Why it's important? Well, I represent the only company, I guess, that really deals in this aqueous two-phase partitioning. The reason is, and that will not be the subject of my talk, I'll be talking only about phase separation a bit later. Just to explain, if you add any biological mixture, it could be cells, it could be cell organelles, it could be proteins, blood, whatever biological fluid. What you'll get distribution of components of this biological fluid between two phases. None of these components will be changed in terms of its function or activity. It will not be the nature. That was shown for everything there is in biology. What our company does, we use it for diagnostics. The idea is that all current diagnostic tests are based on measuring concentration of a given biomarker in biological fluid. And changes in the concentration are supposedly representative of changes in your health status. The problem with that is it works pretty well for infectious diseases, but for the complex diseases such as neuro disorders or cancers, it doesn't work. Basically, it doesn't work because for every one of you, the level of protein, this or that protein in your blood will change depending on whatever excitement you have in your life, your arguments with your partners or traffic jam or whatever. It will all fluctuate. As a result, under pathological conditions, you have changes that are very comparable to what we will observe under non-malignant conditions. When you look at partition coefficient of a given biomarker in such two-phase systems, what you'll see, again, you have to tune conditions. I will not talk about it today, but what you'll see changes in partition coefficient of a given protein will mean that either protein changed structurally, say by glycosylation or phosphorylation or in whatever other way, or that the biomarker started to interact with something, some partner, could be protein, could be some ligand, for which it didn't interact under normal conditions. So the specificity of the diagnostic test is seriously better than just measuring protein concentration. As an example, what we have almost have on the market, basically we should get the FDA decision by the early fall this year. It's a new test for prostate cancer, where the main result is that 50% over about 55% of men could be free of prostate biopsy, because the blood test can tell urologists if it's worth doing biopsy. And a lot of people I talk to who have to go through biopsy procedure told me it's no fun. But that aside, let's go to the phase separation. Now, what we know when we study partitioning of proteins in two-phase systems, what we know is that the solvent properties of the phases, or water in the phases, are different. What does it mean, solvent properties, and how can we characterize them? For that purpose, what we did was based it on studies of Keynote and Taft from 80s, 70s, 80s, and what they did, they developed the Solvatochromic dyes that could measure different solvent properties of various organic solvents. And these properties are three. Basically, what we did, they used it for organic solvents. We selected the dyes that could be used for aqueous solutions. What is Solvatochromic dye? It's the compound, usually aromatic compound, that changes its color going from one solvent to the other. On the right at the top, you can see different colors for different solvents. Of course, in aqueous solutions, the difference are not as huge, so you cannot see a difference in color. But what you can easily detect is how the shift of maximum of UV absorption for a given dye. And here are three dyes we use. One, boron nitroanisole, is used to quantify what is called the polarity polarizability, and that's the characteristic of dipole-dipole and dipole-induced dipole interactions in water. Nitrophenol will provide characteristic of hydrogen bond acceptor basicity of the solvents of water again. And this at the bottom right-hand dyes, they provide characteristics of hydrogen bond donor acidity, or ability of the solvent to donate hydrogen bond. Now, what's good about this approach? First, it allows you to quantify the difference between the solvent properties of water in the phases. And plus, it turned out that these solvent features define a lot of physicochemical properties of aqueous solutions. Basically, what you found is that these two or one solvent feature out of three I mentioned before is very strongly correlated with totally different physicochemical properties, from water activity to viscosity, dielectric permittivity, relative permittivity, surface tension, you name it. Basically, all basic physicochemical properties we could find in the literature from 20s and 30s when I really trod the literature. Everything is quantifiable in terms of these solvent features of water. The important issue also is that turned out, basically we all know, and I was actually pretty stupid not to think about it before, but for phase separation to occur, what we need is to interfacial tension to appear. Without it, there is no phase separation, of course. And turned out that when we measured interfacial tension in aqueous two-phase systems, it turned out to be very well described that these different between solvent features of water in the two phases. Then, of course, the pretty obvious question became, okay, but where these solvent properties are coming from? Where do they originate? And what we looked at, it was already described in the literature, the way of studying hydrogen bonds arrangement in aqueous solutions by looking at the OH-stretch band by so-called ATR-FTIR. That's eliminated total reflection Fourier transforming for that spectroscopy. And the idea is that this OH-stretch band can be fitted by a pretty simple model consisting of 4 Gaussians. Each Gaussian has fixed positions that are shown on the left. And the idea is that Gaussian number 1, this 3080 centimeters minus 1, it represents a subpopulation of water with ice-like structure. Gaussian number 2 represents subpopulation of water with also 4 hydrogen bonds, but with distorted structure. Basically, the angles of bonds is not as fine, as clearly detected as in ice. And Gaussian 3 is the subpopulation of water with 4 and 3 hydrogen bonds. Subpopulation 4 is hydrogen bond from 3, 2, and 1 hydrogen bonds. An extremely simple model. The point is that what we found is that this subpopulation exists in water, and they are kept in the aqueous solutions of different compounds. Only contributions of the same subpopulation change depending on the nature and concentration of a given compound. And here is basically for different proteins where we could measure hydrogen bond donor acidity of the solvent, how it changes in protein solutions. They are very strongly related to this arrangement of hydrogen bond. Basically, it's 2 or, well, here it's both examples are 2, component 3 and component 2 Gaussian curves. Now, for some proteins, that single Gaussian at component 3. But what it means is basically what we showed that in all different aqueous two-phase systems we studied, the difference between the properties of the phases can be described in terms of difference in hydrogen bond arrangement for component 3, this 3400. And it correlates pretty well with the ability of the partitioning ability of the systems. Now here is the final example. It's the system that is formed with boron serum albumin and polyethylene glycol 35,000 molecular weight. For this system, we look at hydrogen bonds before phase separation, and basically the procedure was we took the say point at the phase diagram like here when the system exists, then we mix the phases and run FTIR. Then we diluted this mixture to the 0 and run FTIR at different concentrations. What we observe, yes, here is the for Gaussian second and Gaussian third, they're the largest contributions in the spectrum. We've seen that basically the changes into the arrangement of hydrogen bonds, concentration-wise, happen before phase separation occurs. And that gets some idea about how phase separation happens. I'll show you. The interesting thing is previously what we found was that in two-phase system, dextran polyethylene glycol, the albumin is concentrated in the bottom phase, dextran rich phase. To move it to polyethylene glycol rich phase, we have to add additive, which is in this case 3-methylamine oxide, TMAO. It's a very well-known osmolyte. And this osmolyte doesn't interact with albumin or with polymers. It just affects properties of water. If you add enough, here's for albumin. If you add enough of TMAO, 2 molar in this case, albumin moves completely from bottom phase to the top phase. So as a result, the thinking was, okay, if we can move albumin from one phase to the other, that means for BSA polyethylene glycol, additive of TMAO should destroy the two-phase system, provided TMAO affects only water. It doesn't affect anything. And here is the example. If I'll be able to show it. Oh, I was so proud by this movie. Okay. Just.
You want to show this movie?
Yeah.
Okay.
Under. Finger under here, and then it will appear in the signal. Well, okay, guys.
Okay.
The only way here you have to trust me. That's I hate it, but there's no other way. Basically, what happens when you add TMAO, it destroys the system. Two phases disappear. And we made a movie how it happens under a microscope, where the process is slow because you cannot mix. You just add, and it happens by diffusion. And I hope to show it to you, but not in the cards, I guess. So here are the final. Basically, the idea is that when you have aqueous mixture of two polymers below binodal line, this mixture is not just simple aqueous solutions of two components. It's the ensemble of different water clusters formed by these phase-forming polymers. And these clusters, when you start increasing concentration, these clusters increase in size and in dissimilarity. When the dissimilarity is large enough, the interfacial tension starts to appear, and you getting the cluster size increasing. As a result, you get the point that when the difference exceeds a certain threshold, interfacial tension appears and phase separation happens. And that's it, I guess. Thank you. If you have any question, I will write down. Okay, somebody else now fight with this. Sure.
You mentioned that these polymers don't really like each other, that they don't come together.